All of our hypothesis testing, all of our ANOVA idea asked us to check and see if treatments were related to the variation, if our spread was unusual, if our differences were out of line. That sentence in and of itself brings me to a visual image. I want to go back and change the type of data we are looking at altogether and try and do some different analysis. So let's start with a change to our data. Bivariate. All of the data analysis we have done to date, with the exception of a little bit of stuff we did back in chapter 3 and 4, was based on univariate data. One pile of information. Bivariate, two variables. So now I'm looking at a relationship between the two pieces of information. And one of the things I can ask is, are these two sets of data related at all? Page 462, table 12.3. How long do you wait at the DMV? A long time, right? But it depends on how many clerks there are, how many windows are open. So this person went and looked at different times and counted how many windows were open and what the wait time was based on the number of windows being open. I'm going to use this data to start with. $385, $335, $383, $344, $288. Okay. I have this information. Way back in chapter 3, I said the easiest thing for me to do is to visualize this. Chapter 3 was all about visualizing data. How did we visualize bivariate data? How do I make a picture that goes with this? I promise you did this. I'll go you even a step further. Not only was it in the homework, it was on the exam, the first exam. A scatter plot. A scatter plot turns each of these linked pairs into an ordered pair. and then graph those on a piece of graph paper. And I can get just an immediate preview of what's going on. This table is available in our data files. In chapter 12, it's labeled DMV weight under the exercises, but I put it up as chapter 12, section 3. There we go. How do I make a scatter plot? Aha! I'm inserting a chart. So if I light these up, I can go to Insert, and then there's a whole bunch of chart options, and right there is the scatter plot. It even says X, Y, scatter. And it will assume my first column is X and my second column is Y, but we can edit the data to show this. And when I do that, I get this picture. Number of windows open is horizontal. Wait time in seconds is vertical. I see this. Now, you might intuitively think, hey, the more windows that are open, the less wait I have. Except that doesn't go down as I go from left to right all the time, does it? It went down, it went back up, it went down. But even at 7 windows, my time is not better than it was at 5 windows. So there's a trend here, but it isn't obvious. I could, before I do any calculation, just ask, do you see a pattern? Yeah, I think as I go left to right, this is going down. Wait time goes down as number of windows open up. How nice is that relationship? How strong is it? I mean, I can take averages. The average wait time is 347 seconds when there are 6 windows open. Because the average number of windows, the average of those numbers, that doesn't tell me. That is a wonderfully accurate, useless piece of information. And it doesn't allow me to ask if there's a relationship. Now, I can do that just by looking at the scatter plot. And depending on the scatter plot I am looking at, I can see a number of interesting things right away. So here, on page 457, number of competitive brands carried by a golf shoe company against the annual wholesale revenue. Notice anything strange about this data? What the hell's happening here? They are raking it in, aren't they? I don't know why, but I clearly have an outlier. Aha, that's a familiar term. How did we define outliers before? They were way outside what we considered our normal range, right? Which was based on the average and the standard deviation. So having that average and standard deviation might be helpful when I'm dealing with univariate data. But now I have to look at this both in distance vertically and horizontally. That's just not in line. Median home price versus unemployment rate in 206 different zip codes. What do you think happens as unemployment goes up? The home prices, based on this information. But as I see higher unemployment, I'm seeing fewer high prices and more low prices, right? So I would wager that as unemployment rises, home prices should come down. More people having less money or fewer people having a job, harder to get a home, home prices come down as a result. I can't guarantee cause and effect here. I can just say these things look related to one another. So we have this thing called a correlation coefficient. We did this back in chapter 4. You've seen this before. As a matter of fact, on our scatter plots, there's a direct way to do the correlation coefficient here. There is a formula for manually computing correlation coefficient. I will tell you right now, it is an absolutely disgusting equation. That's nasty. But that's the way you compute correlation by hand. We will not do this by hand. A question for you, though. How many of you have taken a science class that did vectors, physics of any type, trig at any? Some did product for two vectors. We talked about angles between vectors. That number is an angle between the vectors made by my data. Not just an angle. If I go back to that trig class, the formula for that angle involved a cosine. This actually turns out to be the cosine of an angle. Okay, a trig question, and I know trig's not a prerequisite for this course, so I don't know about it. What do you know about the graph of cosine? If you drew the graph, what's it look like? Down, up, down, it wiggles back and forth, right? What's the biggest it can be? 1. And the smallest it can be is -1. This is an angle. It's a cosine of an angle. This number is always between -1 and 1 because it's a cosine. It took me until I realized that this formula was the same formula as the vector formula for me to understand why this was always between -1 and 1. It doesn't just randomly happen to be between -1 and 1. It's measuring an angle, a cosine of an angle. But if I'm looking at this data, I don't see any angles listed here. This doesn't help me figure out where those angles come from. So I go back here and I ask it to correlate this information, to find the correlation coefficient. And in Excel, the command is correl, correlate, equals corr, there it is, correl. And then it asks me for two lists. It asks me for the X list and the Y list in order. So all I have to do is highlight the X list, comma, highlight the Y list. Oop. They have to be the same length. Close my parentheses, hit enter. That tells me a correlation. The closer that number is to 1, the more straight line, direct relationship I have. When one of them goes up, the other one goes up. The closer to -1, the closer straight line relation I have, but downward, inverted. When one of them goes up, the other one goes down. -0.73, closer to -1 than it is to 0. So I have a relationship that is decreasing, a negative number here. On page 459 are a bunch of other pictures of different scatter plots. We've seen this back in chapter 4. That's a positive correlation. As X gets bigger, Y is getting bigger. It's not a perfectly straight line, and that's why this number is 0.9, not 1. Here, yeah, as I go from left to right, most of these things seem to go up, but there's a lot of spread, right? So that lowers my correlation. It isn't a tight line as it was before. This, as I go from left to right, you could be going up, down, side, no idea. There's no correlation. That's why that correlation coefficient is 0. These two are the mirror images of these. A correlation that is negative and fairly tightly grouped, negative 0.9, negative 0.5. But it's this last picture. That says it's got a correlation coefficient of 0. But it looks like that data is related. It's just not related in a straight line. Correlation here is only measuring straight line fit. We can measure other types of correlation. The calculations are much worse and much less reasonable to do in Excel. Directly, we can use these ideas in a different way. There is, if you go to the Wikipedia article on correlation, there is a picture there, I think of 8 different data sets, all of which have correlation coefficient 0. All of them are beautiful pictures. One of them is even shaped like a dinosaur. It measures straight line behavior only. So things can be related, just not in a straight line, and the correlation coefficient won't tell me that. Questions? Our graph has a correlation coefficient, but I only have 5 data points. So I could ask, is this a good estimate of what's really going on all the time? Just like a sample mean was an estimate of a population mean. Just like a sample proportion was an estimate of a population proportion, a sample correlation coefficient, which is what we built, is an estimator for the population correlation. And as we saw in the housing price example, there were 206 counties there. How many counties are there in the US? Once you have your computers open, Google counties in the United States. $3,104. I only took 206 of them. I didn't take a very big percentage, did I? So if I were to do all 3,144 of them, if I were to do a census rather than a survey of unemployment rate by county and median home price by county, I could get a complete survey and I would be able to get a population correlation, wouldn't I? But this is an estimate for that. How confident are you in this estimator? Wait a minute, that's the same question I asked before. Do I believe that the real population is some particular value, or do I believe my sample? This sounds like a hypothesis test or a confidence interval. I should be able to do both. Now, I really want to run a test to see how accurate I think this is. If I believe 2 things are correlated, then I'm going to make a hypothesis about it, and I'm going to test it. I'm back to the same thing I asked all in the last exam. What's my null hypothesis? What's my alternate? When it comes to testing correlation, my null hypothesis is always the same. Our population correlation is going to be this Greek letter R, rho. I know it looks like a P, but it's an R. This is the problem we get switching alphabets. R is an estimator for this rho. If this is my null hypothesis, what's my alternate? That it's not 0. Now, I need to test something. I'll do a t-test. Why a t-test, not a z-test? There are two different reasons here. But I did both when I did probability. I could do z based on certain conditions and t based on certain conditions. What were those conditions? Sample size. I have a very small sample size, right? But small sample size, I can't assume it is a normal distribution, so I need to use t instead of z. The other thing is, I don't know anything about standard deviations here, do I? And I used z when I knew the standard deviation. I don't know the population standard deviation. I can't use z, I have to use t. So I'm going to do a t-test. Now, if I'm doing a t, I need my degrees of freedom. Remember, our t table has all those degrees of freedom lines on them. All right, wait a minute. When we figured out R, I used two pieces of information. If I go back and I look at that big ugly ass formula, I had an X bar and a Y bar in there. So I used my information to compute two numbers. That means I need to take away not one, but two things from my degrees of freedom. I take away one for each thing I already calculated. I calculated X bar, I calculated Y bar, so my degrees of freedom go down by 2 instead of 1. Okay, so wait a minute. I have 5 data values. Quick, turn back to Appendix D, where our t distribution tables are, and find for me the values that go with the degree of freedoms of 3 degrees of freedom. Now notice, what we've got here now depends on alpha, right? 95%, 99%, 90%. What's our sensitivity? What's our confidence level? And since we are setting up those null hypotheses, is this one tail or 2? Because it's equals versus not equals. It could be low or high. That's 2 tails. So I go to the 2 tail line and I pick based on my alpha. I'm going to go with 0.05. In that case, my T critical is 3.182, right? So now I need to know what the calculated statistic is. And there's a formula, just like there was a formula for figuring out what T calculated was for the T tests and Z calculated was for the Z tests. For all of our hypothesis testing, we had a calculated statistic. Even in the ANOVAs, we had that T stat and F stat, right? We had a statistic that was calculated for us. In R, we calculate our T stat as R times. That is not an Rth root. That is R times. I'm actually going to put it in parentheses so it's a little clearer, because when I first realized that I wrote that way, it looks like it's supposed to be an R in the root. It's not. It's a square root. And notice the only number I need to figure out T-calc is R itself. Now, let's do this for our number. Okay, what was our number again? I go back to Excel and I see that our correlation coefficient was, I'm going to call it negative 0.733. Out comes my calculator. All right, from the inside out, n minus 2 was our degrees of freedom. That's 3 over 1 minus negative 0.733 squared. Take the square root of that whole thing, and I'll multiply by negative 733. Let me do that calculation right here. Square root of 3 divided by, parentheses, 1 minus negative 0.733. I forgot the parentheses, 1 minus paren on that. Oop, paren. Because if I'm squaring a negative, I want the square to cancel out the negative. There's the square root. Enter. Multiply that by negative 0.733. Now, I'm doing a two-tail test. What does this number tell me? Keep or reject my null hypothesis? Why? I need to be outside either negative 3.18 or positive 3.18. I'm not. I'm in the middle. I'm not out in the rejection area. I keep this. Now that actually tells me something really interesting. What does that tell me? Let's put this back into our problem setting. Because remember, this is about this data. What does it mean that I did not reject the null hypothesis here? I'd be confident in what? But my null hypothesis said that for the population, correlation coefficient should be.
It should be 0. So they probably.
I'm not very confident in this number. This number might have just been an exception. As far as I can tell, since this is not a big enough group or a strong enough group, this might actually be random chance that it goes down as we go with more windows. Even though 0.7 is really close to 1 by comparison to 0. It's closer to 1 than it is to 0. I can't say for certain how reliable this particular thing is. Phooey. It looked like it was so strong. And then, no. My null hypothesis doesn't allow me to keep this. I did do all of the calculations to do the correlation coefficient by hand. If you're interested, I didn't think you would be, but I put them up there just in case. But please notice, I did the same thing here. There's our t crit and our t calculated value, and they are done. Hey, wait a minute. That t crit right there. Look at the top. That's t inverse. Two tail. The same lookup we did with the table we do in Excel. And then I told it alpha was 0.05, and the degrees of freedom were 3. And then I did our calculated one. Then there's a p-value. What the hell? Where did the p-value come from? Well, the p-value came from looking up my t calculated on a table that we don't have in the back of the book. Back of the book allows me to look up the z's, right? But it doesn't allow me to look up all the t's. It only allows me to look up the cutoff values because the t tables are really, really big if I want to look at all the values. So it doesn't do it. But if I say, what is the t value that goes with 1.865, it'll give it to me. But I multiplied by 2. Why did I multiply by 2? 2 tails. And what do I know about that p-value? It's greater than 0.05. And I can only reject the null hypothesis when p is smaller than 0.05. So in spite of the fact that I thought I had a really good, clear relationship here, I'm not confident in that answer. Now, there is a way to compute an R critical value, but it's not exactly easy, and it doesn't allow me to do anything with my alpha. There's no confidence level there. There's a formula in the textbook. R crit equals T over square root T squared plus N minus 2. I will say with a completely straight face, doesn't help if I don't show you the formula that I just wrote down. I will say with a completely straight face, I've never used that formula, ever. In all the correlative analysis I've done, never used it. But notice the same thing had to be done here that we did in our hypothesis testing. The first thing I have to do, the thing that we had to do on every single one of those questions in exam 3, to know what the hypotheses are. If I don't know what the hypothesis is, I'm in trouble. Questions? Problem 5 asks me about returns in mutual funds. Gives me the last year versus this year. And I could ask, if you earned money last year, How likely are you to earn money this year? Were you likely to go up or go down? How did returns work with each other? And again, there's last year's return percentage versus this year's return percentage. And I can graph those against each other. Please notice one of the numbers is negative. Somebody lost money last year. But then this year they made 12%. Must have done something better. Do you believe that if I did more than just 17 portfolio funds, that I would see a relationship here? How many degrees of freedom? There were 17 funds, so there are 15. So if I go to the 15 line on my T-table, and I say, all right, 5%, two-tail test, what's the T-value that's the critical value? .131. I'm either going to be above 2.131 or below 2.131 with my calculated T to figure out what's going on. Somewhere in here, I believe I did that. There we go. My correlation coefficient's 0.53. You made money last year, you should make money this year, probably. But my calculated T-value is 2.43. Keep it or reject it? Reject it. This correlation should be not 0. I'm more confident this time that the correlation is not 0 than I was in the previous example. By the way, there's the p-value calculated with the same lookup expression. Notice this time it says T distribution two-tail, dot 2T up there. It automatically did the multiplying by 2. I don't have to. Comes up with 0.028. That's smaller than 0.05. I'm good. Questions? For a two-tail test, if my critical value is less than my calculated value, then I'm outside, and that means I do reject. If my calculated value is bigger than my critical value, that's when I reject. Oh, I'm out there in the tails, in the weird part, something weird happened. It's not 0. I printed these. Questions? More questions. Ask me more things. When I have a scatter plot and a correlation, I would then be asked to make predictions. And to do that, I need to know, is there a way to quantify the relationship in my scatter plot? There's the scatter plot we were just looking at. If I tell you that my fund last year had a return of 16%, can you predict what it should do if it matches this idea? Well, 16% is in this big blank space right here. I have no data about a fund that did 16% last year. Uh-oh. So what I want to do is I want to build a model, a linear model. Okay, wait a minute. A linear equation. I have a response variable and a predictor variable. This sounds familiar. We talked about responses to changes in our ANOVAs. Okay, I'm happy to hear those terms come back. I want to come up with an equation. And I want the equation to be the line, because that's the equation for a straight line, that fits this data the best. Air quotes around that are deliberate. How do I define a good fit for this data? And once I have it, what does it mean? All right. Again, I'm not going to do these calculations by hand. But let me work with the interpretation first. On page 465, I've got a number of already given to me equations. Here is a survey of housing that predicts the price of a home based on the square footage of the area of the floor plan. Interesting note, they reversed the order of these two things. They put the B first and the MX last. I don't care, you're adding. I don't care what order you add in. What the hell does this mean? This number right here, this 150. What does that mean? Home prices in dollars, right? Obviously, area is square feet. The units on this number are dollars per square foot. That's a slope of a line. So every time my house floor plan has one more square foot, the price should go up $150. These are expensive houses, but it's not unrealistic. A question. That number, 125,000. Does that make sense? Why not? Well, because I have to pay money for something, right? I don't just buy a house. What else do I buy? The land it sits on, right? So even if I paid for a 0 square foot house, I'd still pay $125,000 for an empty lot. Why are you buying the ground? Technically, you're not buying it. You're buying the privilege to own everything under it. Mineral rights, the land space, and the utility. You own that section. You own what's under it. Somebody comes along, wants to drill. Even if they're doing a horizontal drill, they go under your house, they get to pay you. But now I can say to you, I'm going to buy a 2,000 square foot house. 3 bedrooms, 2 baths, a living room, a great room, and a basement. 2,000 square feet. What should I expect to pay? $150 times 2,000 is $300,000. Add the other $125K, I should be paying $425,000 for that house. It's a lot of money, isn't it? By the way, I know several of your Math of Finance classes will teach mortgages. $425,000, your mortgage payment is roughly $2,400 a month, $2,500 a month for 30 years. And of course, interest rates are going to change this, right? Problem 12, 9 here. Car theft equals 1667 minus 35.3 median age. Theft is the number of car thefts per 100,000 people by state. Median age is the median age of the population of that state. What does this number, negative 35.3, mean? What are the units on that number? Well, this is in years, right? So this number is something per year. Car thefts per year. And it's negative. What does that mean? In states where people are older, the number of car thefts is going down. Why? Older cars. You hang on to a car for a while, don't you? All these 18, 19, 20-year-olds buy those giant Hummers. There you go. More on this on Wednesday. Plus, where the hell does this equation come from? I will see you all then. Have a wonderful rest of your day. Katie, you okay?